Esse é mais um seminário do ciclo de seminário do PESC. A gente tem tentado organizar um seminário por mês, em temas variados. Esse tema é muito quente, se percebe pela sala lotada, e eu vou falar o resto em inglês. Na verdade não vou não, porque quem vai apresentar ele é a Marta.
Ele entende português.
Ok. Já está falando português? Muito bom.
Nossa palestra vai estar em inglês.
Dessa vez, né? Da próxima vez a palestra é em português, é isso?
Aproxima.
Ok. Então, hoje nós temos um palestrante ilustre, mas eu vou deixar a Marta apresentar ele, que vem trabalhando com ele. Obrigado.
Então, eu vou falar em português, a apresentação fica mais fácil. O Patrick Valduriez veio ao Brasil pela primeira vez em 1990, quando a COPPE organizou o Simpósio Brasileiro de Banco de Dados. Ele foi um invited speaker e falou sobre a tese de doutorado dele, que foi sobre paralelismo em banco de dados. Então, quem fez o meu curso conhece o Patrick Valduriez do livro que a gente adota. Então é uma alegria tê-lo aqui. Ele é um especialista internacional, né, em relação ao tema, banco de dados e paralelismo, distribuição, e vai falar hoje sobre Data Science. O professor Patrick, ele é do Inria e colabora com várias equipes internacionalmente. Ele colabora com a nossa equipe já há uns 15 anos. O professor Alexandre Assis, aqui do PESC, foi aluno de doutorado do Patrick e comigo, uma orientação que a gente vem seguindo durante muito tempo. O professor Patrick tem vários artigos premiados, alguns no VLDB, que é a melhor conferência da nossa área. Ele é um membro honorário da ACM, então a ACM Fellow. Em 2014 ele recebeu um prêmio muito importante na França, de pesquisadores que se destacam. É um prêmio também de muito prestígio. E é um professor super acessível. Os meus alunos gostam muito de trabalhar com ele. E ele está sempre nos visitando. Dessa vez a gente conseguiu fazer essa palestra aqui. So Patrick, I thank you a lot for coming here, and I hope we have many other collaborations with other students and we keep on going.
Thank you, obrigado. Obrigado para ser aqui. So now the pressure is on with this introduction. So it's a general presentation of data science, and I will not go deep into machine learning or whatever. That's not the point. The point is to take stock on where we are and see what are the opportunities. There are a lot of opportunities which will even change the world. I see a lot of young people. You will see at the end that there are many new opportunities, but there are also a lot of risk. And it's very important, especially for people like us, because we need more and more education in this area, like in computer science, which is managing our work. Okay, so I start very basic with a few definitions. I'm not asking you what is the difference between data and information. You should all know, but I just repeat it because there's a lot of confusion, especially when I work with companies. They talk about data, about information, and when I ask precise questions, how do you define it, they have a hard time. So, as a matter of fact, it was very confusing even in France, and I was asked to write an article called Les données en question, which is a nice title, Data in Question, with Stefan Grumbach, who is a colleague. So I'm basically summarizing what we are saying. Well, data is something basic, elementary, like room temperature now. That's a piece of data. A grade of a student at an exam, etc., etc. Well, one piece of data can be very complex, a satellite image. But it can also be very simple, like the room temperature. If you just look at one one data item, it's not very useful. What gets very interesting is when you integrate different kinds of data together. So when we do this, we get information. So information is obtained by, you have to work, right? You get data and you do some work, interpretation, analysis, and this will give sense to the data in a given context. So for example, climate evolution, you have to combine temperatures over a long period of time in a given context, a region. The grade of a student at an exam is not very useful, but the ranking of a student, compared with the other students and so on, will give you a sense of whether the student understands or not the field. More important, there is a subtle relationship between data and algorithm. I just let you think of this, which is very related. So the better the data sets we are working with, the better the machine learning algorithm. Because, of course, the machine learning algorithm, they need data to, well, like human being, you know, when you learn things when you're a child, you need to feed your head with data, but not only this. I mean. Okay, 2 milestones. There are many other examples. So 1997, this is really an interesting example. Well, it's a big machine. It's an HPC, one of the first HPC machines. It was used to advertise HPC. It's IBM Deep Blue, right, which defeats the chess world champion at the time, Garry Kasparov. The algorithm is quite old. It's an algorithm. It's planning algorithm from operational research, which was there for a long time. What made IBM Deep Blue beat the champion was, well, of course, there was a big machine. It was able to do 300 million operations per second, but it's because the machine, the program, has been trained with lots of chess games from chess masters. And the most recent result, of course, was last year, where the Google AlphaGo, which was done in Cambridge in the UK, at Google Labs, defeated the Go master, Lee Sedol. That was, and well, I'm not an expert in Go, I just know a little bit, but the complexity, the number of solutions are much higher than in chess. And again, they use a very basic algorithm, Monte Carlo. They use also neural networks, and to train the network to be able to, especially to cut paths that will go nowhere, they train with 300 million of moves. Okay? So it's not just the algorithm, right? It's the algorithm and the data and working together that changes the thing. This is something I like very much because it really summarizes the whole thing. This is called the Continuum of Understanding. So the highest level is called wisdom. So if you understand very well the situation, you can make wise decisions, wise guesses, and so on. We'd like our politicians to have wisdom, right? So it is a continuum. You start with data, so you have 2 dimensions, context, understanding. So you need to understand better and better. So I talk about data and information in a given context, sure. But then you can derive knowledge. And knowledge, like how did we get knowledge ourselves? Or how do you teach knowledge? Because a lot of you are teachers. It's very hard. You cannot just take whatever you have in your brain and plug it into some student's brain, right? Because you need experience. So we have to experiment in a given context and so on. So knowledge is much more general than information. You have general rules, for example. There's a field in data science called data mining. From the data, you will mine in order to get general rules. And the final step is wisdom, which is which really has to do with sharing the knowledge among the combination of human beings and computers. I will go into more details later, because now you can, of course, subcontract many tasks to the computer, but I'm really putting the human in the loop. In fact, it's a word that Marta uses in our joint paper, human in the loop. This is very important. So human will never disappear, but it has to be closer and closer to the computer. So the point here is that, well, if you don't do a good job with data management, the whole continuum is wrong. You will get wrong information and bad knowledge, and of course poor wisdom. Okay, so it really starts with the data. In fact, at the level of capturing the data. Okay, so I didn't say anything so far. Let's get to the point. So I will introduce data science. I will tell you a number of stories, which I call the good, the bad, and the ugly. And then I will talk a little bit about technologies. We are right now in a workshop on HPC for energy. In that context, we are dealing with HPC and big data, so I will zoom on this because there's joint work with colleagues from Brazil, COPPE, LNCC, and I will, the important point is number 5. Okay, so data science. It's interesting because everybody understands data and science, but putting the two together, you can have many different meanings. So, well, very simply, it's the science of making sense out of data. Technically, it means using, of course, data management. The first data science is really statistics, right? And statistics, well, it can date back to the old Egyptian, but it was defined in the 18th century. And in statistics, there's an important term, which is state. It was just to be able to count people in the state so that they could pay taxes, things like that. So that's very important, right? All the countries work that way. Machine learning, visualization, human-computer interaction. And the goal is to collect, clean, integrate, process, analyze, and visualize big data. So we'll have to zoom on big data. You cannot do data science without big data. The ultimate goal is to create products and services for data management. So we have a new breed of worker called data scientists. The term was quoted by one of Obama head of science, whatever. And we need people who understand statistics, data analysis, machine learning, data management. So who is able to understand all this? And because remember, wisdom, experience, context mean application domain, right? So I'm calling this the business domain in a general sense. But the application domain can be very complicated. And this is very important if you want to interpret the results and draw a meaningful conclusion. So data scientist is hard to find. And it's like a sheep with 5 legs. There are new training programs all over the world, started in the US as usually. Well, now, for example, my colleague Michael Franklin, the guy I used to work with when I used to be in the US, was a professor at Berkeley. He moved to Chicago to create a school which will integrate different schools to do data science. So, mathematics, data management, and so on. There was a panel session at SIGMOD. SIGMOD is a big conference, well, number 1, like VLDB, where, well, in fact, my field is database, but everybody thinks it's boring, so now I say data science, everything thinks it's cool. So, big data. So what is it? So, well, like data science, very much a buzzword. Well, very interesting. You know, when I give a presentation, especially when people from industry, they come at the end and say, well, I have So they give me a number of terabytes, 50 terabytes. Can I say that I'm doing big data? So I say, well, it depends how much do you give me. Well, it really depends on what you're doing with the data. So for example, 10 terabytes for a transaction processing system with very compact data is very big. But for a web search engine, it's very small. So it really depends the kind of data and what you do with the data. So there's this definition from Wikipedia, which is good, but it emphasizes only big, which is size. Size is only one dimension. But if I look at size, how big is it? Again, it's a moving target. Terabyte, we are talking about zettabytes now. So in the 80s, when I went to work in the US, I got to work with this machine, Teradata. Teradata was targeting 1 terabyte. Nobody could do that at that time. Right? And in 30 years later, Oracle came up with a machine called Exadata, this machine. So it's a moving target. It will keep going that way. So in other words, in the 80s with Teradata, we were already talking about big data. In fact, the conference Marta mentioned, VLDB, means very large database. Okay. But today's situation is very different because we have been talking VLDB and so on about structured data, well-organized data. Well, we have exponential growth of the data produced by all kinds of tools, programs, networks, devices. For example, number one is, of course, the one that you know, Web 2.0, social networks. Nobody can produce any kind of data. Not very useful sometimes. That's the point. How do you get useful information from all this data? Mobile devices, computer simulations, satellites, etc. At the same time, we have still increased storage capacity. So, for example, it has doubled every 3 years since 1980. But look at the price. Just looking at HDD, forget about SSD. 1 gigabyte in 1980 was $400K. And today it's 1 cent. Okay, so you can store everything. In fact, I was in a panel session maybe 20 years ago at SIGMOD in the US, and there were people from NASA, and they were saying, well, you want a lot of data. Well, our satellites, they keep pumping data, but we don't know what to do with it. We don't have enough storage. So the problem has been solved by this. We can keep everything. And this is very useful, of course. So not only the size is important, but there are other dimensions. So I talked about the first dimension. So we call it the V's, the 3 V's, the basic 3 V's, but there are others. So volume refers to massive amounts of data. So the issue here is how to store, organize, manage the data. Number 2 is velocity. You have continuous streams of data being produced by sensors, for example, and you want to, well, the traditional way has been you get the data, you put it on storage, and then you run your application. Well, what if you want to do online data processing? As the data comes in, you want to make decisions. Variety. So you have different data formats, semantics, uncertainty, multi-scale data in science. Means that getting useful information needs to integrate heterogeneous data. This has been a very old problem, but it gets really hard today. So semantics in particular. And there are other V's like validity, veracity, volatility, and some others. So a specific aspect, which is really the key in data science, is what you call also BDA, Big Data Analytics. So the goal is to find useful information and discover knowledge. Okay, think of this continuum. Typical use, forecasting, decision making, etc., and the traditional techniques, data analysis, data mining, machine learning. It's much harder than what used to be done in traditional database management system for, well, several reasons. The first one is probably the most important one. there's very low information density. It's like in corporate data, for example, in a bank, in a reservation system, all the data has been really controlled as high value. If you grab data from the web and so on, you will have a lot of junk. So it's really like searching for needles in a haystack. Okay. You really want to be able to pick pieces of data. You have external data. So how do you trust this data? You have fake news today, right? And in fact, this is an issue. Some of us are working with newspapers in France too on these issues, how to automate the analysis of news. Different structures, so streaming time series, data from sensors, for example, in geology and so on, how to integrate. And I will go next into these issues of machine learning. That machine learning is a very hard field, but you need experts. If you don't know very well, then you can do big mistakes. So typical application, what I call the killer applications. Of course, the big one from the web giants, Facebook, etc., social network analysis. So the issues are to deal with modeling, simulating, visualizing large-scale networks. Online fraud detection across massive databases. So online, not after the fact. So this is true in e-commerce, banking, telephony, national security, cyber analytics, for example. This is something that Marta is doing here. Real-time processing analysis of raw data. Well, for example, to detect changing external conditions. These fields are completely revolutionized by data science, healthcare, medical science, where you can have personalized medicine. It's very interesting to see that the companies which are behind the new startups are companies like Google, Amazon, and they have nothing to do with Medicare. But they know how to deal with data. So in our group, called Zenith in Montpellier, where we are dealing with data-intensive science and scientific data management, where essentially in one slide we get data that comes from various appliances, so observations, data that comes from experimentation, for example, an HPC platform, plant phenotyping platform, this very famous one in Montpellier. This brings data. We also take care of the human beings. So the scientists, for example, are typically organized in social networks. They publish papers also, so you find a lot of data in the papers. And basically, we have a box here which process, integrate, analyze, search, and produce all this. So this is something pretty old, from 2004, which says, well, the problem in data-intensive science is that scientists are spending most of their time dealing with the data, where they should do science, right? If they do biology, they should really do biology. This was recognized in 2004. We have a project for a lab in Montpellier called in French, Institut de Biologie Computationnelle, Computational Biology Institute, if you want. And some speaker at the last review said that in bioinformatics, the time spent, well, answer the question, the time spent to deal with the data was well above 50%. Because I have to deal with, they have to access also the databases which are online to compare and so on. It takes a long time. So it's really a big challenge. Well, now time for a couple of stories. So you all know what this is? It's very old. Well, I'll start with the good news. Well, the good news is from Europe, because we do good things in Europe. So you all know the LHC, Large Hadron Collider, which is a big instrument. It's a big ring, 100 meters under the earth, several kilometers at CERN. So this is discovery of the high boson. So this is really big data. They deal with 15 petabytes of data. This collider produces 15 petabytes of data, which is analyzed by different labs to verify theories. And there are about 200,000 analyses at the same time. In 2012, CERN announced that it had discovered a particle that was probably a Higgs boson particle, which is predicted, right? It's been predicted for a long time by the standard model of particle physics, but this was just a theory. So so it took them, scientists, they take their time, they check everything. And it has been confirmed in 2014. So that's a big thing. I think only this result justifies the investment in this machine, in this instrument. Well, Google sponsors such things. So you all know the Google AdWords and AdSense programs. This is where marketers can have their results advertised when you do a search request. It is very big money. It is 15 billion a year of revenue for Google, which makes it the #1 marketing company. Whereas initially it was just basically a search engine. It's the #1 marketing company. So with this program, the user defines its maximum cost per click bid that she is willing to pay for a click on a ad. So how it works, it's quite complicated. It's at runtime, based on all this information and the keywords from the search request. It's a competition for marketers to win access to consumers, more precisely for models of consumers, because they don't know precisely who's going to give the keywords, and their likelihood to respond to the ad, and determining the right bid for the item. And this allows Google to rank the ads in, usually on the right-hand side, but now and it's a big data application, 30 billion search requests a month with 1 trillion events of history between search providers. Okay, so there are many good stories that you can find. People don't talk too much about the bad stories, so there's this interesting article, when big data goes bad. So this one is interesting. So this is the search with screen capture. You know this one of with Amazon. And so someone is looking for this book, which is the book of obscure book in genetics, and you find two prices. One is used $35. And the new version is outrageous. So why is that? In fact, as you all know, Amazon is not just a seller, it's also a platform where everybody can sell things. So here, Prof and Bodybook are selling platforms. So what happened? This is just an excerpt. So there are two programs run by the sellers, Bodybook and Seller, which engage in an incremental bidding war. So once a day, Profnet would raise their price to X times. Because obviously there were not too many occurrences of the book, maybe a few, maybe just one, I don't know. Several hours later, Bodybook would increase and it would keep going. So it's like the subprime crisis. Very stupid model. In fact, oversimplified model. So reality is much more complex. The human being would see this is a mistake. So this is the danger of having everything controlled by algorithms and big data. This one, very interesting. It happened to me. The day before yesterday, preparing my talk, I double-checked. So I went to amazon.fr, and you can see that my address, mon adresse de livraison, is Brazil. So I did this from here. And I just said Patrick Valduriez. So you get, well, Marta, thank you for the publicity. So this is a good book, but there will be a new version next year, 4th edition. Okay, so far so good, right? You can find me. Okay. Well, the next page. Well, I like rock, right? So it's okay, and that guy is okay. But I didn't write these books. So this story has been going on for years now. So the first time I was checking on the price of my book and comparing with other stores, and I discovered that. So I was quite surprised. I even asked my daughter. I have a daughter who is a musician, and she's a rock player, and she's famous. So I said, well, maybe there's something wrong with this. And she said, no. So the problem with Amazon, you cannot go in Montpellier and go to an Amazon store and start yelling at the manager. Right? There's no telephone number. There's no even email. So I had to do some search. At some point, you find in Amazon a warning saying, well, basically, everything we give you as a result can be wrong. So, but if you find something wrong, just tell us. So you can. So I filled the form, left my email address. So then they say, okay, we'll take care of the problem. And 1 month later, they said it was okay. I did the same request, and this result was not part of the final result. So I said, okay, end of the story. And 3 months later, I did the request. It went back away. So, although I have the right to get rid of this, I cannot get it fixed unless I go. Obviously, there's a matching problem because they integrate data from all kinds of subcontractors. So there's no way I can get it fixed. Although in Europe we have the right to. So every time I will ask them to fix it, they will fix it, but it will come back the next day. Okay. So it's okay, because as long as it's Ozzy Osbourne, it could have been much worse, right?
You are gaining audience, maybe at the expense of losing credibility.
Yeah, but even this, how would I get a job in a business school? Well, I used to work in a business school, so I know that. But it's, because human resources, they look at how you are on the web. This is called a 360-degree vision, right? Okay. The ugly. There are women in the room. Well, this is a T-shirt that used to cost £14, between 14 and 16 pounds. Keep calm and rape a lot in Amazon UK, which is of course politically incorrect. Right? It was on sale. So there was a company in the US which was behind it. They were selling it on solid gold bond. So of course there was a big campaign against this company, and they got bankrupt. So what happened? Well, in fact, the company did everything automatically, right? So they use machine learning and all these techniques. So they use library of words, and they try to put them together, like keep calm and carry on, all those that you can find everywhere. But they did a mistake here, and they overlook a single word in a list of 4,000 or so. Okay. So the problem here is that they have context-independent model, but here, when it's like translators, the translators, they just Google Translator for translation, for example, which is quite good. They look at combination of words, but the words are just bits that are together. They have no meaning. So that's really an issue for these techniques. Okay. Next, how am I doing with time? Oh, okay, so I'm fine. So a few words about technology now. So the data science landscape is quite complicated. So you have, so it started in companies usually because companies, they want to make money, and so it used to be called business intelligence. It's very interesting because data science, this will be the conclusion, will push us to redefine terms like intelligence, artificial intelligence and so on. But anyway, so analytics, visualization. So you see the big players that I mentioned, Teradata, Oracle, etc. But you also have, I'm not going to explain too much, these new technologies, and I will zoom on this. So what's called the data processing framework, like Spark, Hadoop, NoSQL databases, and so on. But anyway, it's easy to get lost right now. There are many diverse solutions, no standards, many products, a lot of open source keeps evolving, which is normal. It's nature, natural selection, and so on. It's how things have to move forward, because nobody knows what to do, basically. What's very important from a data management point of view is that the traditional software stack in database management is basically the database management system controls everything from the memory to the disk. So it doesn't use a file system. And in fact, the early database management system, which were implemented on top of maybe Unix, use the Unix file system, and they were very inefficient because the file system were not designed for database management. The situation has changed. So today, we have this the stack where we have distributed storage. So typically, the data is not stored in one place, it's stored in a distributed manner so that you can get parallelism. And on top of this layer, you have either database management system functionality, so it's called NoSQL. You also have NewSQL, or which gives you a high level of genericity and independence from the data, or data processing frameworks, so that programmers can really program very complex machine learning, whatever analysis they want to do. And on top of this, you can have query tools, analytics tools. So the best example of this architecture is Hadoop, which is very famous in big data. And sometimes there's a confusion between big data and Hadoop. It's not really the same. There are other ways to do this. So for example, in Hadoop, the data is stored in a distributed file system where the data is split into pieces, chunks. So this comes from Google, actually, which had a project called Big File, and there's the Google file system, which allows to do this. On top of this, there's a scalable database management system called HBase, or the data processing framework like MapReduce, being replaced now by Spark, meaning that you can program all kinds of analysis functions in your, well, in Hadoop, the language is Java. Programming language have been impacted also by data science. So Java is kind of a low-level language. It's better than C, but still low-level language. Spark, for example, from Berkeley, they use a new language which comes from Europe, Scala, which is a functional programming extension of Java. And in our group, we use Scala, and if you take a Java program on Spark, which is that big, in Scala it will be that big. So it increases the productivity. And then you have tools like R, which is a basic tool for statistics, Mahout for machine learning. So I'm not saying much on the technology, just saying that because we have this new software stack, there are many new ways to deal with data management. And in particular, when we deal with HPC and big data analysis, so Traditional HPC, well, basically data management is based on files and so on. When we combine the two, the idea is to use data-driven models and to be able to produce knowledge out of the thing. So to have a better combination to automate some processes which are typically done by experts. But it's a hard field, as we see in the project we are dealing with. So more generally, I talk about data-intensive science. So there's a book by, well, the work was initiated by Jim Gray at Microsoft, and then this is a book called The Fourth Paradigm, which says basically that modern science, astronomy, biology, computational engineering, and so on, well, the only way they can make progress is by dealing with a lot of data. And this scientific breakthroughs, example of the CERN before, will be powered by computing capabilities that help researchers dealing with these massive data sets. So in this particular case, well, we have to integrate two paradigms, HPC, which can mean, for some people, it means specific machine, like the machine here at NACAT from SGI. So that I would call this high-end supercomputer, but you also have compute clusters that you can get in Amazon or SGI, for example. SGI has an offer of HPC in the cloud. And the other paradigm is what we call data-intensive scalable computing. So Hadoop is one example, but you have a lot of different frameworks like Spark, Pregel, this is graph processing, Giraffe is graph processing, Pregel is from Google, NoSQL and NewSQL databases. So if I compare the two, HPC and disk, there are different dimensions. So for example, HPC has been essentially used for compute-centric application, jobs that last a lot of time, hours, days, weeks. Whereas disk is really data-centric. The applications initially are different, science and engineering, HPC. Disk has been very popular in web and business data processing application, which is why it's really an issue for people who want to do data management in HPC, because they don't find people. For example, all the people trained in my group, they would go to web business data processing companies because they get so much money. So that's really an issue that we are trying to change. So different targets, so simulation, well, there are many other things you can do with HPC, but simulation, whereas in disk it's data analysis. The major difference, as I understand it, the number one objective in HPC is performance. So for example, predicting the weather, well, if you're today and you predict the weather for tomorrow, you cannot spend 2 days. So you have always a limit. Whereas in disk, performance is important, but that's not really the main thing. Scalability is important, fault tolerance, availability, and cost performance. This is why we use different machines, share nothing clusters, which are easier to maintain. Programming models, of course, the only way to get high performance is by being close to the hardware. So there are low-level interfaces to do parallel programming, like MPI, OpenMP, but there are also a lot of operator libraries. Whereas if you look at the data processing frameworks I mentioned, well, they are typically based on functional programming languages, and you have functions like map, reduce, filter. In database, this is called relational algebra, and with an algebra, you can do transformation, you can reason, you can do many things. The languages are also usually different. You find a lot of C, C++, maybe some Fortran here, whereas here you have Java, Python, which is a very popular language, and Scala. A major difference also is the hardware. So typically the disk is shared, whereas here we use share nothing clusters of commodity hardware. So some advertisements. So we have the HPC for Energy European Brazilian project. Here you can see the flag. which is ending in November. So, for example, Stefan, who is here, is heading the work package where we do data management. So the bottom line is that there are different approaches to do data management. Typically, people have been doing post-processing, so they get all the data, they put it in another machine, and they do the analysis. Well, this is good, but you can only do batch analysis. In situ analysis is very interesting, is that you try to run the complete this software stack on the supercomputer. Therefore, it's somehow intrusive, but then you can do interactive analysis and deal with the simulation more directly. There's some compromise, which is called in transit. So you offload the analysis to, so it works very well in a cluster, for example, where you would have different nodes, compute nodes, data nodes, and you could combine them. We have a very interesting European project right now with Bull called the CloudDB appliance, where we exploit new technology, like, for example, remote direct memory access, RDMA, which allows a node to directly access the memory of another node. And this is done now through networks, fast networks like InfiniBand. So this creates new problems like synchronizing simulation and analysis. So we had last week a workshop of the side disk project, which means scientific data analysis using data-intensive scalable computing. It's a joint project between my team at Inria, Marta's team at COPPE, and Fabio Porto at LNCC, and two associated universities, UEFI, which got started in 2017. So we'll be continuing on this in this area. Okay, so time to conclude. So opportunities and risks for whom? So you are all computer scientists, so I'm gonna just stay in IT, information technology, so meaning information systems, but then I will try to be a little bit more general. So the opportunities for information systems, well, essentially cost reduction. People have been using traditional data warehouses. They are very complex. They take a lot of time to set up. So that's the number one reason that big companies are moving to this area. Second reason, which is obvious, but this was the reason of data warehousing, faster and better decision making. In particular, a killer application is online fraud detection, for example. There is also data crowdsourcing, which is used to produce good information. Better knowledge discoveries. This is the virtuous cycle that I discussed before between machine learning and big data. And then, this is very important, you see new data products, new services, and new companies. So, for example, what the economists call two-sided markets, markets where two different kinds of agents have an interest to be together. So the companies there are really mediators, like Uber, put together their ads in the street here in Rio de Janeiro, where they put together drivers and customers. Airbnb, in France, Le Bon Coin, which is a very big success, etc. But it's already having a big impact on, for example, new applications, digital health, digital agriculture. In Montpellier is very strong in agronomy. We have a new project in digital agriculture. Well, the risk. Well, the first one is data security, right? Because the bigger your data, the bigger the target it presents to attackers. The attackers have a limited budget, so they will prefer always to attack a bigger target. So that's why, the intelligence agencies are typically attacked. Related issue is data privacy. For example, personal data can be misused by people who have some responsibility. So that's very important when you do data science, when you're a programmer, a user, an administrator, you have to follow rules, and there's law. So for example, several months ago, there was a trial of someone at Uber who tracked, so he used the super user mode to track journalists who were writing articles against the company, and this is illegal. So we have to be careful with this. Of course, there is a cost advantage before compared to data warehousing. It's used to be called, it's called data lakes. But getting managing big data also has a cost, especially if you want to invest in data security and privacy. It's our solutions, but it's really costly. Well, the major problem, as I see it, is this one: is that people who are developing the applications don't, well, except the big players, Google, Facebook, and so on. They have the top engineers in the world. They have social scientists, so they really know what they do. So they work well. But if you look at everyone's using analytics, you have oversimplified wrong models, misinterpreting patterns. So all this continuum of understanding, which is really badly used. And what I've seen a lot is people dealing with, well, in fact, they keep all the data because they don't know what data should be kept, and then it's really a big problem. So that's more for the computer industry and the users and so on. But what impact on us? Well, the tools which combine big data, machine learning, whatever. So what we call data science. They are more and more intelligent. And well, it's hard to define intelligence. Well, you can go back to the traditional definition. Even AI has been, well, there's the Turing test of an AI, as you all know, which is probably not sufficient. But today we have self-driving cars. In 10 years, they will be everywhere, I'm pretty sure. Autonomous robots, digital assistants, drones, Terminators, you know, like in the movie. 2 years ago at the AI conference, the top researchers, they wrote something saying, well, we don't want tools to have the freedom of deciding to push the button. But it's doable, right? Like in the movie. But of course you have problems. Well, who is responsible in case of a problem? You know, the famous problem of the self-driving car and this emergency situation, and 2 people here and 1 people there. Where should we go? Who should we kill? Well, collateral damages. If you remember the first version of the Terminator movie, at some point, the robot needs to kill someone called Sarah Connor. Just take a brute force algorithm, takes the list of all the people, and just kill them one by one. So it's called false positives. Well, the worst is probably we have to face. It's been a big debate in the presidential election in France. You know, about the well, some people recognize that sooner or later there will be, well, of course, there are no jobs for everybody, and we'll have to deal with a jobless society because we'll have self-driving cars. We have so self-driving car means, well, Uber is already doing self-driving cars because they want to get rid of their drivers. It will be cheaper. So how do we deal with this? And of course, and probably the worst is in fact, I was reading just this morning in the French newspaper that there are studies about how people behave now on the web, and we all know that we are watched. and our behavior is different than if we knew that we were not watching. Right? So people, it's becoming a major issue. And well, now it's not really science fiction. I'll give you an example, but we are talking about transhumans, augmented human. So the definition is that genetically, artificially, genetically augmented, or human just with pieces of here and there, you know, that you can see. So there are many questions, like the end of natural selection, because today it's possible that to choose, you know, what kind of children you want to have. We will have a new human species. Well, this was tried in the, you know, World War II. The Nazis, they tried to push this. So it has been there, but today the tools are very powerful. You know. Imagine what could have happened if the Nazis had access to all this technology. Immortality. I was just reading a couple of days ago that a journalist whose father was dying created an AI program. With all the information, with all the data and so on, and now his son is able to talk to an AI, now that the father is dead. And of course, so these are really fundamental questions, but all what we are doing, because I'm pretty sure most of you will have to work in this area, you will have to be faced with these more basic and philosophical questions. Okay, that's the end of it. This is just art. No way to do. No explanation. Okay, thank you. So please give your what you're feeling. You know what's missing. I mean, it's a very interesting field. So I'm sure there will be comments. Who starts? Fabio, Marta, as usual. Yeah, Fabio.
So you mentioned this HPC and this thing. And so if we consider the models which are behind this, like physics-based models, machine learning-based models, so what would you say about these two? The different perspectives and predictions and so on?
Yeah, so the way I see it, because I'm not an expert in the HPC models, but the people use very precise models with PDEs, partial differential equations, and so on. So we have a specialist here. So I would say it's a very naive answer, but it's relatively easy. Well, because you know when you go to mathematics, then it means you have reached a level of abstraction where you can reason and so on. When you talk about machine learning, well, we already know that, well, for example, comparing images, right? So I take a photo of Fabio, for example, and I will search the web and will find you in all kinds of situations. There will be false positives, there will be good matches, but there will be a lot of errors, right? I can find you in a weird situation, in fact. So machine learning has to deal with this uncertainty and so on, which is controlled by the human being, right? In terms of, well, maybe Stefan or the HPC people could comment on this, but the uncertainty you have in physics and so on is much more precisely defined, isn't it?
Can I comment on this?
Yeah, sure.
So we use models not for only the beauty of the mathematical models.
Can you say where you're from?
Yes, okay. I'm Christian from Total, and I work in Brazil for about 3 years now in the Libra project in the Applied Technology Division. And but I have a background in basically inverse theory. So we do these models because for objectives of
precise
of effectively predicting, forecasting the behavior forecasting the weather, forecasting the oil production on the field, etc. And then the problem is that we can have very precise physics and very detailed physics. But we still need, even if we have a very precise mathematical definition and very accurate modeling, still we need to populate all those parameters. And to populate all those parameters is the objective of basically inverse problem theory. And it's even more complex to solve the inverse problems, moving from the observations to the parameters of the physical model, than to model the data from the physical parameters. And the moving to a data-driven scheme with deep learning methods, etc., ignores basically this and uses the data to make sense out of it in a much more direct way. So it's a real different approach, especially for geoscientists like me that have been immersed into this difficulty of inverse problems from the beginning. It's a real different approach, which is very promising, and probably we can hybridize both.
Yeah, I was going to ask this because something similar happened in Montpellier. There's Inria. Inria is like Embrapa in Brazil. So we work with people doing plant phenotyping, and basically they use statistics and they analyze the data in a very precise way. And now they are faced with big data, and statistics doesn't scale up. So they wanted to use data mining. So it's like, and so we're working with them. Florent Massegli is working with them at finding. So data mining is can deal with big data, but it's not very precise. So trying to put the two together is an open issue. So what you're saying is interesting, Fabio. It means that at some point we could maybe try to combine the two, because the techniques and the approaches are completely different. So that's something we like to pursue.
And when I started digging into this, I thought that a good analogy for these deep learning would be like a sort of giant interpolator that you can predict something which is, you have millions of data, so you can predict a situation that falls in between observations. But if it's a different behavior, you cannot predict it. But in fact, if you use typically like Bayesian formulations, you can predict the probability of not happening. So you can also have insights into information into events that you have not sampled. So it's actually quite rich.
So one issue with deep learning is the quality or whatever, how you define it, of the training set. Because we are faced with this, we have an application called PlantNet that we developed in our team, which, well, basically with your iPhone you take a picture of a plant, but not here in Rio de Janeiro, in Europe, because the plants are different, and it will try to tell you what it is, and but it does mistakes, of course. So the way the models are trained is very important, and of course there are already a lot of issues. Recently there was a beauty contest by an AI, and the title of the article was "Can an AI be racist?" And why is that? Well, because of course, everybody could send a picture, and there was a ranking automatically, and mostly white Caucasian people were selected, and because of the training set. Okay, it's not the algorithm. So algorithm without data, well, go back to the saying that I put initially, is not useful. So yeah, the two together is very important. In fact, it's because I've been working on data forever. I've been writing algorithms and so on, and doing this presentation, I really feel that it's something really to emphasize, the two together. Other questions?
So, talking about the transhumans.
Yes.
There is one American guy who's officially transhuman. I don't remember his name. He saw the antenna over his head, and he has the daltonism, very serious case of that. He could not distinguish color, but he can hear the colors. So he transformed the electromagnetic energy into sounds, and somehow they fuse that in his brain and he hears the colors.
Yeah.
So I mean that brings another way of looking at data. So we can hear colors. We can do whatever we want, like using LSD.
Yeah. In fact,
and that's data science too.
Yes, yes.
And it's going to have a much more iconic approach than simply a data-driven.
So the data science is extremely powerful. In fact, well, it has not been translated, but there's a book by Serge Abiteboul, famous data expert in France, and Gilles Dorec. It's called in French, Le temps des algorithmes, the time of algorithms. And at some point, they say that in terms of immortality, well, an information system is immortal, right? Well, the company will probably die before the information system. You can keep the data forever. It's just a matter of course, you have to replace the disk, and the technology will keep changing. And it's already true. There are companies which have been here for 100 years, and you can get the data. Then you may say, well, could we just dump everything, which is in your brain, your memory, on a disk and become immortal? But if you look at neurosciences, I don't think it's true, because our memory is not only in our brain, it's also in our cells. So, because the idea would be, well, like in the movies, you just plug to another body, and then you can live forever. So anyway, but people are really working on this. It's amazing. Any other questions? Comments? Yes.
There is one it's not exactly Big Brother, but it's about well, we've been moving from a world where finding information was sometimes difficult. Well, the oldest of us as students, we've been having to go through specialized libraries to find certain specific information, etc. Whereas now so much information is accessible. The problem is that there is a wealth of information that is not verified, that is or sometimes incorrect or even completely false, be it an error or be it a deliberate, intentional mistake. So is there a way by which artificial intelligence could also help us sort out the relevant information, because we are all in quest of verified, genuine information. We don't want 1,000 informations on one topic, we want the one that has the right information.
So in fact, in Montpellier, not with my team, there's another team which is doing data science as well. They are more in the semantic web. And they have a new project with a bunch of, it's in France with some newspapers so to deal with the fake news in a more automatic way. So they're already, if you go to Libération and all these newspapers, they have, how do you call it, detox? Because there's intox, and the opposite is detox. So yes, but right now it's really human labor intensive, because context is very very important. But there are a lot of tools that people are being developing. So there will be more and more tools. My feeling is that human has to be in the loop. Otherwise, it will get out of control. Like the examples I've shown. People think computers, algorithms are well. It's a good saying in the book of Serge and Gilles. They say, well, we are much more demanding on algorithm. We want them to be perfect, whereas humans are not perfect. Like a self-driving car, we would like to have self-driving cars that don't do accidents, whereas humans do a lot of accidents, right? They get drunk and so on. But human error is socially accepted. Well, to some extent. Whereas, so that's why the definition of AI has to be revisited. Artificial intelligence, well, there are the false positives, of course, but usually you can check. But so the combination of that's why transhuman is also interesting. It may also mean a human which is, well, as you were saying, which is because we all have sensors, right? Natural sensors. We can be augmented with artificial sensors. So there are very interesting questions. So what I think is that everything will make progress. The bottom line is which kind of society do we want to live in, right? Of course, all these tools, Big Brothers and so on, for dictators, some countries, I'm not going to say because I'm being taped, so I may have problems later. But some countries, of course, are experts to deny the truth. And also with respect to the data. Working with Stefan Brunbach, he's working with social scientists and so on, and they, in their talks, they say, well, if you look at maybe Amazon, Google, and Facebook, they know much more about France, so very detailed about the French society and so on. They could do a lot of study than the National Institute of Statistics, INSEE, which has very partial information. And in fact, I know that this National Institute now they are making deals with these big companies to get the data. And if you go to Africa, it's much worse. Yeah, so, and information, well, if you remember this book, information is, you control information, you control the world. Right? So that's really, it can be frightening, but so that's why we need, well, what is the solution? One word, education. That's the only word, education. So we need to spread the word and educate people, especially the young people. But people must be computer literate. And it's really an issue, because in France we had to fight to get computer science being taught in the high school. And still, it's not for all, it's just for the people specializing in science, which is wrong. Everybody is, algorithms are everywhere. So it's important to understand this. Well, thank you, everybody.